Okay, our next speaker is Hongguang from the FIU Erlangen-Nuremberg, and he will speak about regular black holes and their relationship to polymerized models and mimetic gravity.
Okay, thanks for the introduction and thanks for the invitation. I'm very happy to have this opportunity to present our recent works. So it's a really new work, it just appeared yesterday, so you can check on arXiv. Also, it's based on the other works. This work is mainly in collaboration with Christina, Param, and Stefan, who is a PhD student in our group. So from the name, you already see it's a regular black holes and their relationship to polymerized models and mimetic gravity. So actually, it's very nice. We can introduce many things we are using this model, and we are able to answer some questions from Carol, Madwan, and also the Oppenheimer-Snyder. Okay, so this is our main motivation. So we have classical regular black holes like Buddy and Hayward. They coming from couple some strange matter field to GR is pure classical. Final one, I would like to say. We also have the quantum black holes, for example, the one inspired from loop quantum cosmology and loop quantum gravity. The main question we would like to answer is, can we have a unified framework that be able to describe and investigate both kinds of regular black holes? Like, can we marry the classical ones, where we already know from Buddy and Hayward, and the quantum black holes we have from loop quantum gravity? The answer is yes, if we extend a little bit our definition to the our definition of the polymerization function to more generic class of functions. More generic class of functions, I mean we extend it from the trig geometric functions, we extend to arbitrary functions. We'll see what I mean by that. And I would like to say this formalism is really is more or less used our formal developed formalism about embedding LTB into polymerized models. I think some seminal works are done by Boyova at 0809, but later on there's not so many works. Of course, now LTB is hot, becoming hot again. Yeah, so let's give some background. So we start with the classical regular black holes. So these are regular black holes, which, as I said, is GR plus usually quite exotic matter field. And the most famous ones among them is the Buddy ones and Hayward ones. So if you look at the metric, so we write the Schwarzy like metric in this form, where GR is this curly G. So we know the Schwarzy metric is just RS over R. That's the easiest thing. So what Buddy and Hayward did is just slightly modify the denominator. So still keep them in the same power, but slightly modify the denominator such that when R goes to 0, there is GR is still finite. So this is a simple trick to get a regular black hole. And of course, I mean, every metric is Einstein equation plus some matter field plus the corresponding energy momentum tensor, so you can explain it. And these models are quite, because they can be understood as GR plus no linear electrodynamics. You can write out a no linear electrodynamic action to give this two kind of regular black holes. And then you need to identify this parameter to some electron charges. But we have questions. First of all, it's GR regular black holes. Can we relate them to quantum gravity or quantum geometry? That's the first one. Second one is what are the more physical situations, for example, the gravitational collapse, because these are simply static metric. The third one is also about this. So we know GR has Birkhoff theorem, which states that the vacuum solution is uniquely given by asymptotically Schwarzy. It's an asymptotically static solution, actually. But this, I mean, from the explanation, they are not vacuum, but they are static. Can we relate to some vacuum things if we have a quantum gravity theory? And final question is perturbation, because they are still in classical GR. So all perturbation theories are classical GR perturbation theories. And so the main thing is, can we relate them to a more general effective QG framework, effective theory from quantum gravity. Another motivation is about quantum black holes. We already see many of the talks during yesterday's parallel section and also this morning Vika's nice plenary talk. So we would like to have some regular black hole models from background independent quantum gravity, of course. So we know to extract observational effects. For example, Thomas Tima in his plenary talk already discusses. We need a relational framework such that we have an observer to define our time, and we also need, for black hole models, we also need an emergent space-time in the continuum description because we are dealing with black holes. It's 1+1 differential theory. Deep quantum, of course, it's okay, but to describe semi-classical physics, we still want to have some GR language. But usually it's really hard to derive these dynamics from a four theory perspective. So what we did is symmetry-reduced models. We all know that we have the loop quantum cosmology and also loop quantum black holes. These are inspired from the four theory, and we just use them to derive effective dynamics in the homogeneous space-time and also in the 1+1D with some gauge fixings. So there are plenty of works on this line, but still it's not so satisfactory. The first thing is we cannot encode quantum gravity effect to perturbations. They are still symmetry reduced. Everything is subject to the symmetry reduced space-time. Another thing is always the problem of general covariance because somehow polymerization will break a little bit the general covariance, and this makes coordinate transformation impossible if we do a relational framework. If we first gauge fixing, then we are subject to that coordinate. We are no longer be able to transform the coordinate unless we regain the general covariance. I have a small comment that even the algebra is closed, the coordinate transformation are generally not the classical GR coordinate transformations because the algebra is modified. We are not in the standard algebra which reproduce the Lie derivatives. The final thing is how to consistently embedding a dust collapse model. There are already plenty of works. Also, Vika talked about this. One thing I want to mention is that because we are in a modified, it's not classical GR anymore for this effective series, the junction conditions are generally modified. It's no longer again the classical ethereal junction condition because that's a junction condition derived from the weak solution with general relativity. So this can be changed. Another thing can be changed is the Oppenheimer-Snyder models. It also may be changed because it also rely on the junction condition. Okay, so our solution to this thing is we find an effective 4D high derivative covariant Lagrangian with LTB embedding. LTB embedding ensures that we still have the decoupling for dust collapse and Oppenheimer-Snyder works. And effective 4D high derivative covariant Lagrangian makes it possible to do coordinate transformations and regain covariance at this level. So this is basically our result. It's a summary already at this level. So what we propose is we have a relationship between the extended mimetic theory, which is a modified gravity with high derivatives, and also polymerized Hamiltonians. And we add the LTB embedding into them. So what we have is first this high derivative. It can contain infinitely many high derivative terms. So this somehow is relevant to the UV completeness of the underlying quantum gravity theory or symptotic safety. And also here is a mimetic theory. There is a mimetic field. I'll tell you immediately what is the mimetic field. It plays the role of an observer, so it defines our time. And also, as I said, we have the LTB embedding. We allow decoupled dynamics, such that we have decoupled equation motion with dust within the dust comoving frame, and this allows Earth to glue along dust geodesics, which is the Oppenheimer-Snyder model. And we also have some more advantages. So we can prove a Birkhoff-like theorem for this model for the polymerized vacuum. So we have an answer to our previous question. And it allows to reconstruct the theory consistently from the static metric or from the cosmological solution. I didn't write it. It allows the reconstruction consistently. The reconstruction, of course, contains a reconstruction about the field Hamiltonian and also the 4D mimetic Lagrangian. And in this framework, because we have this 4D mimetic Lagrangian, we can explain the regularity, the appearance of shocks or not, is there any singularity appears or a limiting curvature mechanism, and then we can answer them in the curvature invariance. And also, we are naturally encode the inhomogeneous dust collapse because we have a decoupled equation motion. And also, we can find exact inhomogeneous dust collapse solutions by solving the modified freedom equations in the LTB coordinates. They are just the inverse functions of an integration. And finally, let's remark that we assume the effective dynamics captures the main quantum effect and is hold for all radius. For example, it's also hold for radius at 0 because this is essentially what happens for Badian and Hayward. Okay, so let's now move to the more technical part. What is a mimetic gravity theory? So this is the mimetic. Sorry, let's use. This is a mimetic gravity theory. So it's a classical GR plus what we call the mimetic constraint. But if we look at this constraint, it's nothing else but no rotational dust action. So the mimetic field is no rotational dust. What we add is this extra high derivative coupling term. And this high derivative coupling term is a contraction of all the high order derivatives of the Fermi nu, so it's second derivative. And then contraction of second derivative gives you all high order derivatives. But one remark is that there are only two independent terms if we want to study spherically symmetric spacetime. So we all restrict ourselves to only two independent terms, which is K1, K2. And if you write the modified Einstein equation, you found a very nice property. So this modified Einstein equation can be rewritten in this way. So we have the classical GR, but now we redefine a new modified Einstein tensor. And this new modified Einstein tensor is the classical GR plus all the high derivative couplings from the mimetic field. And then on the right-hand side, we still have the standard no rotational dust energy momentum. So we have a natural explanation that this is an effective theory of gravity coupled to no rotational dust. And this will be more clear if we do the Hamiltonian analysis. If we move to the gauge fixing, I just want to say that the gauge fixing is consistent. We can just do phi equal to t gauge fixing. And what we obtain is this. So in this phi equal to t gauge fixing, it's a unitary gauge, and we fix Lapse function equal to 1. This is because of phi equal to t, if you want. And what we got is a physical Hamiltonian. Well, maybe not physical, but at least a Hamiltonian with temporal gauge fixing. And if you look at the form of this Hamiltonian, it's nothing else but the most general polymerized Hamiltonian we can propose. And this F function encodes all the polymerizations of the mu-bar scheme. So it's naturally also encodes the mu-bar scheme. And this is just a simple Hamiltonian analysis. You can always rewrite the Hamiltonian analysis of this theory, restrict to symmetry, spherically symmetric spacetime. You see in this form. Of course, we don't give the detailed form of alpha, so this f alpha, the polymerization function, is completely determined by alpha. Or worse, the alpha is completely determined if we give a detailed form of f of our polymerization function. Okay, but now we have a natural explanation now with this dust thing, because if you look at this C alpha, this scalar part of the Hamiltonian is equal to the dust density multiplied the volume. This is also our classical explanation of the no rotational dust couplings. So that's why we call this, we still move this part on the right, we move this high order derivative terms to the left to define our modified Einstein tensor. And this modified Einstein tensor is compatible with this polymerized Hamiltonian. But you see this, the model is still very general. We have too many polymerizations. And also we allow for polymerizations beyond the loop-inspired models. So it's still too general. And now we have we want to give some restrictions as I said. So it's LTB embedding. So what is the LTB? Space-time is the Lamont-Tolman boundary coordinate. If you think that it's a dust field driven collapse model. So dust field is pressureless. So if we go to the dust comoving free means dust is the free falling observer. And then we have the orthogonal slicing for the x coordinate. And each dust trajectory is geodesic. They are the free falling observer. And in this one, it means that each x trajectory is constant. So every dust, they have a constant trajectory, and this is dust collapse. So every dust has constant trajectory means somehow we have a decoupled equation motion for dust. They do not talk to each other. There is no interaction with them. So in this coordinate, you can write out the Hamiltonian. So this is classical. I just go to the marginally bound case. I will ignore. So no marginally bound case, basically I choose this curly E equal to 0. So if we go to the marginally bound case, it's a very simple way to write the Hamiltonian. The Hamiltonian also decouples. So this is the classical Hamiltonian constraint, or a physical Hamiltonian if we want, a scalar part. And it can be written as a dx over h tilde, and h tilde is nothing else but our cosmological Hamiltonian. So now the dynamics of 1 plus 1D field series does collapse. In this way, it's partial differential equation, but now it really becomes single cosmological dynamics for each dust particle. We don't need to solve the partial differential equation. We only need to solve this ordinary differential equation. And we all know the solution is the solution of the Friedman equation. So if we write out the solution of the Friedman equation, and we got this, I think many of you already know this, is Sx minus t with mx. And what is mx? It's a conserved quantity, because this is a cosmological Hamiltonian, is a mechanical Hamiltonian. It has a conserved quantity. And this conserved quantity is the mass inside each dust shell. So it appears as solution. And if this conserved quantity is a constant, it doesn't depend on x. And we say C is 0. This is what? This is the vacuum. So the vacuum is this mx equal to 0. And if we go to this mx equal to 0 part, we see now this solution, which is R, is only a function of xx minus t. It doesn't depend on xx plus t. So what it means? It means we have a Killing vector field. And you can show that this Killing vector field is time-like asymptotically. Actually, it's time-like in all untrapped regions. So this is the Bikov theorem. We obtain a unique asymptotically static solution. Okay, so it's very nice if we can go to the RTB coordinates and have the decoupled dynamics. But you know, but this is for classical theory. For polymer theory, this is for most of the theory is no longer true. And for many theories, we even cannot do the decoupling. There's no decoupling anymore. But luckily, we found a subclass of the polymerization which still allow us to do similar tricks. And you can find details in our previous paper. So what is this subclass? This subclass is actually the following. And it's a subclass of the model which we cannot do any kx polymerization. And also now the polymerization can be rewritten in this way. We have two polymerization functions, which is only the polymerization function of the mu-bar scheme of the k-phi. And also this polymerization function, they have some relation that I just listed here. And you all see why it's like this. And also we can re-express from this Hamiltonian the corresponding mimetic Lagrangian. Here I just write the mimetic Lagrangian as the 1 plus 1D mimetic dilaton model, but it's the same as it's the same as the 4D version. And here, because we only polymerize the k-phi, if you look at this, I introduce x, y, which are functions of k1, k2. And this polymerization of k-phi is actually only appears as the polymerization of this y function at the mimetic Lagrangian level. So we only polymerize y, so it's nothing to do with x. And one more thing is that we want to have the decoupled similar dynamics as classical one. And we don't have it. It's really similar to the classical one. It's still dx h tilde. The only thing is now we get an accuracy-like thing. It's polymerized cosmology on the decoupled dynamics. So everything follows. It's just now this b square becomes the function b. So you can solve all the black hole models now just as you solve in cosmology. This is the nice property of this model. And also, we still have this conserved quantity here. It defines the mass. Okay. This is the marginal bound case. I want to comment that we can also do this in no marginally bound case. In the closed universe, for example, I don't want to list it here. It's more complicated. Okay. And now let's look at the dynamics. How we do dynamics? It's cosmology. So it's, I mean, every x is independent, so we only need to look at one x. And we know this is, now it's really a no-linear dynamics. And all the dynamics is determined by a phase space trajectory. And if we look at phase space trajectory y, we draw a phase space trajectory in this one. So v and b, they are phase space variables, but we draw a 2gm over v with b. And if you look at this 2gm over v, is nothing else but our polymerization function. So this already tells you that all dynamics are determined by this polymerization function. So it's really different kind of polymerization functions gives us different kind of dynamics. Now we have two mainly difference between these polymerization functions after we generalize it. So if the polymerization function is monotonic and it's unbounded, we don't have a bounce. When we have bounce, if it's bounded, it means we have a minimal value of v. That's why we have a maximal value of 1 over v. So bounce means we have bounded polymerization. And every bounce happens when the polymerization function has a local maximum. That's the thing. And we even can solve for each segment, since if we give out the analytic form of the f, then we can write out the modified Friedman equation, but it's only on each monotonic segment, because for different segments, this modified Friedman equation can be different. And if we write out that, we can just do a simple integration and inverse to get the solution for the R function. And the R function defines all the metric in the spherical symmetric spacetime, because it's RTB metric. And if you look at this, it's very similar to what happens, in classical one. So we have the same argument. It's not working. Sorry. Yeah. I don't know why it's not working, but let's use this. So it's a very similar argument that how we obtain a Birkhoff-like theorem in the polymerized theory. So it still is a function of sx minus t, not a function of sx plus t. That's why we still have the Birkhoff theory, Birkhoff-like theorem, let's call it. Why we call it Birkhoff-like is more clear from here. So now this is RTB coordinate. We have the underlying covariant theory, so we can do coordinate transformations. Let's transform from the RTB coordinate to the tau R coordinate, which is the Schwarzy-like coordinate. And what we found is that this coordinate transformation can only be done for each single monotonic segment. And if you do this, you find you may got different Schwarzy-like solutions for different segments. So this gives us the two different statements for the Birkhoff-like theorem. The first one says we have a unique asymptotic vacuum solution, but it's RTB coordinates. And in this coordinate, the solution is unique and asymptotically flat, which we ask for the asymptotic classical region. They have the classical GR behavior. And we have extra killing field, which says that it's asymptotically static. But now if we go to the Schwarzy coordinate, it's no longer unique, but we may have countable many. And each Schwarzy-like solution, they correspond to a piecewise monotonic segment here. So actually they are connected to the solution in the RTB coordinate, because the solution in the RTB coordinate is analytic and it's unique. Okay, one more thing is, in which case we have a unique Schwarzy-like solution, is when we don't have a bounce, of course, there is only one segment, so we have only one Schwarzy-like solution. Another special case is the symmetric bounce. If they are the symmetric bounce, these two segments actually give you the same solution. That's why we still have a uniqueness in the Schwarzy-like things. Okay, I need to be fast. This gives us the reconstruction theorem. If you want to know details, just to see our paper, I just want to see, we can start from arbitrary, all these errors, they are double, so we can start from arbitrary thing to reconstruct the force theory to derive all the dynamics in other case. So for example, we can start with the Shirazi-like metric to reconstruct fully the model and derive the general LTP solution and the inhomogeneous dust collapse. Or we can start from cosmological solution, redo all the constructions here. We have a Shirazi-like metric and also the underlying model. Okay. One last thing I want to say before I go to examples, if I still have time, is the limiting curvature mechanism. So this answers the question why we still have shockwave solutions or weak solutions. It's the following. So we have a Lagrangian, and then we have a Lagrangian expressed if we want this potential is expressed as x and y. So let's go to a special coordinate. It's still LTP coordinate to express x and y. And then we can express all the curvature invariants as a function of x and y. So if we look at our potential, we can put the polymerization function can put a constraint on y because this is F2 inverse. So if the F2 function is bounded, it restricts the possible domain of y. So we can give a bound to y, but we don't polymerize x. So x can still diverge, but if you look at when x will diverge, is r prime equal to 0. So r prime equal to 0, x will diverge. And then if you look at this thing, this will cancel out because it's exactly this part, so it's still r prime. So when r prime diverge, we have a divergent. We could have a divergent scale, curvature scalar. I mean, I say could because it can be cancelled. I mean, it can cancel in this case. Okay, so this means if x diverge, there is a singularity appears. But what is x diverge is r prime equal to 0. And what is r prime equal to 0 means? It's a shell crossing singularity. So we can already taught us this. So so this means if we restrict y, there is no central singularity. All singularities relate to r prime equal to 0, which is a weak singularity, is a shell crossing singularity. But this happens only when we have a bounce. The reason is for bouncing solutions, somehow shell crossing singularity is unavoidable, except some very special cases. I'll show you why is that. But for no bouncing solutions, like the Badin and Hayward, shell crossing is really the classical shell crossing, is just with slight modifications. So we can avoid this shell crossing in the no bouncing solutions by choosing a good matter field. But for the shell crossing in the polymerized model bouncing solutions, we cannot generally avoid them. They always appear. I'll tell you why. And also I have a remark that if we also put bound to x, we remove all the singularities, but then we don't have RTB. So it's really a choice. Okay, sorry. Now let's quickly move to the example. This is a very simple example with the standard LQC, also T-man regularized LQC. What I want to show this example is, so if we look at standard LQC, the symmetric bounds. So that's why the metric in the Shirazi-like coordinate is unique. But if we move to the T-man regularized LQC, we have two. There is a plus or minus. Corresponds to this branch and also an unsymmetric branch with dashed line. Because it's unsymmetric bounds. So we have two Shirazi-like metric if we go to the Shirazi-like coordinates. And one more thing I want to give is, if you look at this, it's like that we still have the singularity, but in our model, no, because this is GR square. It's naturally restricted by this, by the positive of GR square. And then this gives a bound. This gives a minimal value to the R. It's exactly the R minimum you derived from the other polymerization function or the marginally bound solution. Similar thing happens for the T-man regularized LQC, and you can derive R minimum, but now it's more complicated. So we said that even you give out the Shirazi-like solution, we know if we have a bounce or not. It really depends on if GR square can be 0 or not, or can go below 0. It can never go below 0, and if the right-hand side can go below 0, it means you have R minimum, you have bounce. Okay. And another thing is about the shell crossing singularities. First thing I want to remark is in RTB coordinate, all the geodesics, which is dust trajectories, they do not stop at the bounce, and they do not intersect after the bounce. So they can cross the bounce, even the bounce is a weak singularity. And this Penrose diagram is given by this nice picture by Johanna, already studied in 21. But But one important thing is the shell crossing singularities. So if you look at the curvature scalar, this is the Krejcman scalar. And what happens is that there is a denominator, and the denominator is some positive thing. This is a positive thing plus a linear in Z. And what happens is that this Z can take values from, can take any values in the real line. Okay, this means that there is always have a pole. It always have a pole in S. But there is a special case that in standard LQC, when Z equals to 0, which has a pole, it cancels with the numerator. I didn't write out the numerator because it's long. So this is really a special case. But in unsymmetric bounds, we don't have this special case. And you can see that even at vacuum, we still have a shell crossing singularity, because it always happens in this case. And the final thing is I also show a reconstruction example from the Buddy and Hayward. I just want to show a case with Hayward. You can see what Hayward, for Hayward, the polymerization function is not sign, it's not bounded, it's a sinh. So this is Hayward. And you can also do all the constructions, and you can write out explicitly the marginally bound solution. It also contains the sinh and coach, and also the curvature invariance. And if we look at now the curvature invariance for Buddy and Hayward, why they can avoid shell crossing singularities, that this eta here can only take values larger than 0. It means that if m prime is larger than 0, s prime is larger than 0, we don't have a shell crossing singularity. This is exactly the same formula as classical GR, because classical GR you just replace is in this form. You just replace eta with z is classical GR. That's how shell crossing appears in classical GR, and how shell crossing can be avoided in classical GR. Okay, and also I list some mimetic potential for Alcocer and Hayward just to see we can reconstruct. And one more thing is, if you look at B, which is F2, the Y is bounded by tanh -1. We know the tanh has a value taken from -1 to 1. That's why Y is bounded. So this is the limiting curvature mechanism, and it's more clear from this picture. So both Buddy and Hayward, for smaller f2, which is a derivative of our polymerization function, they go to a constant. They are bounded. That's why from the limiting curvature mechanism, we have a bounded, we remove the central singularity from our arguments. Yeah, that's all I want to say. We go to a summary. That now we really have a unified framework that can describe both classical regular black holes and quantum black holes. And our reconstruction algorithm, we relate the 1+1D effective black models to the mimetic gravity for the covariant Lagrangian, and we can do regular cosmology, which has the exact RTB solutions, and we can do regular black holes, which we have the Birkhoff-like theorem, we have a Hongguang dust collapse, and also we have a limited curvature mechanism, which gives you when we have the regular black holes. And also now this opens many new possibilities. And with this, I just thank you and end my talk.
Thank you very much, Hongguang, for the nice talk. I see already one question from Carlo. I see one from Jonge, Jurek, and okay, I see many. I will go one after the other. So maybe Carlo start, then Jurek.
Yeah, thank you, Hongguang, for this overview of different things and these results. There's one thing I don't understand, given you had this. How much of this survives if one keeps in mind that two things. One, there is Hawking radiation. So the outside is definitely not stationary, or whatever happens after the collapse. And so the question is, how much should we take seriously that these are the possibilities, given that we know there is Hawking radiation? And second, given that we have reasons to believe that whatever happened at the end of the evaporation, it's non-analytic in H bar. It's something which seemed likely to be of the kind e to the minus something over H bar, so tunneling or non-perturbative things. So how much of this should we take it as what is available, given that we know the world has this other phenomena?
Yeah, and thanks, Carol, for this very nice question. For the first one, so here are only we mainly studied the stationary solution, but actually we have a 1+1D or 4D mimetic theory which covers. Sorry, I jumped too fast. So we have the Lagrangian, which is exactly a mimetic dilaton model, and is provide a nice model. I mean, we can even do the CGHS extensions provide us nice model to study the Hawking radiation in this framework. Then we have a really dynamical black hole dynamical horizon. It can be studied in this framework. Just provide the initial condition, provide some null dust or null scalar field, and we can study them. I mean, it's a very interesting next step for the framework. And then we really have the dynamical thing. And for the deep quantum regime, as I said, so this theory only, of course, captures the main quantum effects like LQC. We ignore all the subleading quantum transition possibilities. Of course, when we go into, for example, for the bouncing models, when we go into the deep quantum regime, this is still possible. But this provides a nice semi-classical description or initial value problem, maybe, for the quantum transition. And it's also nice, yeah.
Okay, then we move on with Ansong.
Thank you, Hongguang. So it's not a talk. So I just want to say, when you introduce the high-order derivative terms, normally you have a ghost. How do you avoid the ghost problem?
This model is very special, actually. So how you avoid the ghost is actually from this. Sorry, let me use the pointer. So from this mimetic coupling or mimetic constraint, there is an extra hidden symmetry, because if you can do a conformal transformation of the matrix, the theory doesn't change. So this gives you extra constraint which cancels the extra degrees freedom. That's why it works. So this is a very special model which propagates only 2+1. In general, we know we have the so-called degenerate high-order scalar tensor series where it's always proposed 2+1. How to achieve this is that we make sure that all the kinematic matrix is degenerate. Then we have extra constraints. These extra constraints will cancel the degrees freedom. For this theory, it's similar. So that's why it's subclass of OD host. But this theory is very special because you can really write out the conformal transformation, which is also a gauge transformation in this theory. Yeah, thanks.
Jurek?
I understand that your framework is very, very general. So probably the equations which were at the previous talk, they are a special case of your equations. And in that case, Luca Cafaro and myself, we looked for static solutions, and we found 2-parameter family instead of 1 parameter as in the usual Birchhoff theorem case. So do you agree with this or not? I mean, does this result agree with your result?
Yeah, I mean, I need to look into details, but in principle, our model can also do 2-parameter families of solutions. I mean, it's not forbidden by our model, so it's possible. But of course, your result is no marginally bound case.
Okay, I understand that what is not forbidden is possible, but, but this is not the way we formulate. Birchhoff theorem is formulated.
Yeah, I agree. So from my since in our LTB framework, we can also do no margin. Sorry, too fast. Where it is? Yeah. Since in this framework, well, this is only marginally bound case. For no marginally bound case, we need to add extra no marginal bound terms. And then in our model, how we do this Oppenheimer standard is you write out this one with extra no marginal bound terms. It will also appears here, which is the curly E, which also appears in Vika's talk. And after that, we need to derive the equation motion with the curly E, for example, for what happens in the closed universe. And in that one, the modified Friedman equation is more complicated to solve. This is exactly we add the curly E. So the modified Friedman equation is more complicated to solve. And from here, the solution is, I mean, it's not unique. even for the symmetric bounds, because it's high order equations. So we can have several solutions from this point of view.
So when does this Birkhoff theorem apply, which is here on this slide?
You mean what? This one?
Yeah.
No, but you know, in classical theory, what happens is the vacuum theory, the vacuum solution is directly related to the no marginally bound case. Vacuum solution is never marginally bound case. That's what happens in classical theory. This is always no margin. Sorry, it's always marginally bound case, not no marginally bound case. No marginally bound case will not give you a vacuum because here you have this curly E which depends on X. After you take derivatives with respect to that, you get zero. You get no zero. Unless in some very special cases you get zero, otherwise it's not vacuum anymore. Because here we have a clear notion of what is vacuum, what is not. Yeah. Okay.
Okay, we maybe have time for 2 more short questions.
Yes, a short question. So can you get non-static vacuum solution in this general model?
Yeah, you can, all the Oppenheimer standard extension and all the inhomogeneous extension is naturally encoded in this model. It's just you need to, if you retain it in another coordinate frame, you need to transform it to this coordinate frame. For example, this is a marginally bound solution, which is not static anymore. You have the matter field enters.
Okay. Right.
And this is the most general analytic solution. You just need to do the coordinate transformation to transform it to your familiar R coordinate if you want.
Okay, okay, thank you.
Okay, and then I saw one more question there. Oh, Madhavan also. Okay, yeah, go ahead, Madhavan. Sorry. And then, no, Madhavan, you can, and then we take your.
Okay, so no, I'm not familiar much with the mimetic gravity, but in GR, if you look at the differential equations and you compute their characteristics, then this completely matches with the causal structure. So nothing travels faster than light. So in this case, when you have a different from GR theory, is it possible that you would get superluminal propagation effects?
We still have a constraint if we study the propagator, but generally this will modify a little bit the gravitation wave, the wave equations with the parameter. But we know if we want to relate this parameter to quantum gravity, that's very tiny. It's negligible at technical levels. Yeah.
So, last question.
Yeah, if understood correctly, for some choices of the mimetic model, you can avoid the bounds, right? The first question is only in vacuum or also in the matter part?
Also in all the part, if you look at this, the marginally bound solution.
Okay, so if we are in the matter part and we consider homogeneity, for example, we should expect to recover cosmology, right? From the model. I mean, not LQC in general.
Yeah, in general it has.
So in that case, we for that kind of choice, we wouldn't have a bounce, a cosmological.
No, we don't have bounds. We still have a regular cosmology because if you look at the theta, if you look at Bardeen or Hayward, they cross approaching the theta, you have the theta crew. So it's asymptotic with the theta.
Okay. And in that case, one could avoid the shell crossing singularity.
Yeah. Yeah, okay. If you choose the gold matter field, you still have the same one as classical GR.
Thanks.
Okay, then let's thank Hongguang again.
Yeah, thank you.
Hongguang.